Yeah, very good morning to one and all present here. I, Dr. Ashwani Kumar Dubey, on behalf of our Honorable Founder President, Dr. Ashok K. Chauhan sir, Honorable Chancellor, Dr. Atul K. Chauhan sir, Vice Chancellor, Professor Dr. Balvinder Shukla Madam, entire MIT family, and my own behalf, I extend my warm welcome to all the dignitaries, participants present in this international research seminar on innovations in optoelectronics, organized by Embedded System and Robotics Research Group, Department of Electronics and Communication Engineering, MIT School of Engineering and Technology, and Institutions Innovation Councils, MIT University, Uttar Pradesh, Noida. Welcome you all. I am feeling honored to introduce our keynote speaker of the session, Dr. Annalisa Bruno, who is a senior scientist at Energy Research Institute, Nanyang Technical University, Singapore. The world ranking of this university is 13th. Dr. Annalisa Bruno received her BS, MS, and PhD degree in physics and applied physics from University of Naples, Federico II, Italy, where she also worked as a postdoc in physics and chemical engineering department. She joined Imperial College London as a postdoctoral research associate and studied about organic and hybrid materials for optoelectronic applications. During her scientific career, she has also been visiting researcher at Lawrence Berkeley National Laboratory and the Clyde University, UK. In 2011, she became a senior scientist at Italian National Agency for New Technologies, Energy and Sustainable Economic Development. In 2014, Dr. Bruno has joined the Energy Research Institute at Nanyang Technical University as a senior scientist. Since 2017, she is coordinating the thermally evaporated and tandem solar cell team in Energy Research Institute at Nanyang Technical University, Singapore. And the aim of her team is to develop highly efficient large area solar cells. So her list of achievement is too long. So now I would like to invite Professor Dr. Abhay Bansal, Joint Head, MIT School of Engineering and Technology, MIT University, Uttar Pradesh, Noida, to say a few words, sir.
Thank you, Dr. Ashwini. On behalf of our Honorable Founder President, Dr. Ashok K. Chauhan, Honorable Chancellor, Dr. Atul Chauhan, on behalf of MIT School of Engineering, on personal behalf, I welcome you all in International Research Seminar on Innovations in Optoelectronics, which is organized by Embedded System and Robotics Research Group of Department of ECE. I welcome Dr. Annalisa, who is Senior Scientist with Energy Research Institute, NTU. We welcome you, madam, and thank you very much for sparing your valuable time to be with us. As we discussed, we are looking for some collaboration because a lot of work is happening in this field. I'm sure our research group, which is at ECE and your Energy Research Institute, we are looking for long-term collaboration. I also welcome all Vice Chancellor, Dean, Head of Institution, faculty and students from all the campus of MIT Higher Education and School, and also from other government and private university. Just for your reference, Dr. Annalisa, today MIT has 10 universities in India, and another 2 universities are coming in Chandigarh and Bangalore. Just to mention, we have 17 global campuses, having campus in US, London, and we also have campus in Singapore, Dubai, Mauritius, China, Abu Dhabi, South Africa, Romania, Nairobi, Tashkent, Paris, Sydney, and Russia. Just for your reference, we have 170,000 plus students, 6,000 plus faculties, and MIT University has filed 1,300 plus patents because we believe and we always say MIT is research and innovation driven university. So we have very high focus on research, and we look forward your association in future. And we have tie-up with top 200 plus universities in the world, and we are also accredited by WASC. We are the only university in India, and we have accreditation of QA UK. Our engineering program has been ranked 32 by NRF, which is a ranking by Ministry of HRD, Government of India, and we have been top private university in Uttar Pradesh. And our engineering program are accredited by IIT. And I'm happy to mention here, MIT University has been ranked among top 3% by QS and Times Higher. So with this, I welcome you once again, and I'm sure your talk is going to give a lot of insight and will open a lot of thought among all our students and faculty who are working in this area. And we look forward, because in MIT, any activity we do, we want to make an impact on the society, and we want to make world as the best place to live. So we look forward your mentorship, your guidance to a small group. As we have discussed before also, we can make a small group which can be led by Dr. Ashwini and Dr. Pradeep, so that we can work together and impact our society at large. We welcome you once again, and it is a COVID time. We are doing it virtually. As you told that you have not visited India, could be post-COVID when all situation will be normal. We would like to welcome you on our campus, which is world-class campus which we have in Noida, and we look forward to have your many more visits in times to come. And my congratulations to Department of EC for organizing such a wonderful session on Saturday. There cannot be any good event and party on Saturday having listening to Dr. Annalisa. So we welcome you once again, and thank you for sparing your valuable time to with all of us. Thank you.
Thank you,
Thank
sir.
you.
Thank you, sir, for your inspiring words. Now, I would like to invite Dr. Pradeep Kumar, Deputy HOD, Department of Electronics and Communication Engineering, ASET, MIT University, Uttar Pradesh, Noida, to give his opening remarks. Welcome, sir.
Thank you, Dr. Aswani. A very good morning to all of you. And I hope you are all well and safe during this pandemic. On behalf of Electronics and Communication Engineering Department, MIT School of Engineering and Technology, MIT University in Noida, I welcome you all in International Research Seminar on Innovation in Optoelectronics. And I also welcome to the speaker of this talk, Dr. Annalisa Bruno, Senior Scientist, Energy Research Institute, Nanyang Technical University, Singapore. The topic of the today's talk is very important, and it has a lot of application in various fields. The metal halide perovskite are one of the most promising active material for optoelectronic applications such as photovoltaic, light emitting technology, X-ray detector, because of their excellent optoelectronic properties and thin film fabrication versatility. In the photovoltaic domain, in less than 10 years, perovskite solar cell have achieved a record power conversion efficiency of 25.5% and an increasing growing operational stability also. The rapid progress has triggered the interest in transforming an existing technology from a typical laboratory small area perovskite solar cell into a large area solar cell module necessary for their industrial applications and building integrated photovoltaics. In this talk, an overview of the recent research activity on halide perovskite material from the synthesis to their optical and electrical properties, and finally to their integration in solar cell will be provided. The talk will also present different technologies explored to scale them up over large areas toward industrial applications. Now, I would like to give a brief overview about the Department of Electronics and Communication Engineering. So, Department of Electronics and Communication Engineering offers undergraduate and postgraduate programs. Under the UG level, the program, we offer the Bachelor of Technology in Electronics and Communication Engineering, Electronics and Communication Engineering in 3 Continental. We also offered here the robotics program under this Bachelor of Technology program. And we also offer the PG program, the Master of Technology in ECE, in embedded system, as well as in wheel side design, as well as in wireless communication. And we also offer here EC weekend programs also. Apart from this, we have also offered the PhD program, and Electronics and Communication Engineering has a curriculum aligned with the requirement of Industry 4.0, and it encompasses the cyber physical systems, Internet of Things, IoTs, IIoTs, artificial intelligence, and cognitive computing also. And we are also having a high quality faculty, highly qualified faculty, as well as honorary professors. Globally, a benchmark curriculum on BTech ECE. We have here BTech EC IET UK accredited, and we have on-campus industry-sponsored labs, Atmal MCU Center, as well as Intel Lab, as well as we have also having here integrated employability and skill enhancement courses, skill certificate course by Electronic Sector Skill Council of India, ESSCI, as well as the Telecom Sector Skill the Council, like the TSSC, as well as the Telecom Certification Program by ZTE Telecom Limited. And our faculty has published more than 1,000 Web of Science or oblique Scopus indexed research papers. The Electronics and Communication Engineering Department has a rich tradition in the teaching, research, as well as in innovation. And the research interest of the faculty members covers wide areas of applied and fundamental aspects of electronics and communication engineering. And the department has several research group like the Signal Processing Research Group, the Communication Research Group, VLSI and Microelectronics, as well as like RF and Microwave Research Group, Embedded System and Robotics Research Group. And also we have executed several funded projects funded by DST, DRDO, ISRO, etc. So this is all about the EC department. So now hand over to Dr. Ashwani. Thank you.
Thank you so much, sir, for introducing our department to the audience. And as you well said, that metal halide perovskites are one of the most promising active material for optoelectronics applications, which is being used in photovoltaic, light emitting technologies and X-ray detectors. So you well said. So to listen more about the research and finding in this particular area, I would like to invite Dr. Annalisa Bruno to enlighten us, to give her seminar and share the key findings. Over to you, Dr. Annalisa. And once again, welcome.
Thank you. Thank you very much, Dr. Ashwani, and thank you all the Amity committee for the kind invitation. It's my pleasure today to share with you all our research at Energy Research Institute of NTU. And I will start sharing my slides. Can you see my slides?
Yes, yes.
Yes.
Okay. Okay, so as it's been kindly introduced by all of you before, my talk today will focus on the metal halide perovskite, and I will try to explain you why this material is so exceptional for an exceptional semiconductor for a different wide of application. In particular, me and my team, we focus on photovoltaics application, and so we realize solar cells, and we scale up the solar cells from small area devices that are typically done in the lab to large scale device in order to think to the application in building. This is this image that you can see here on this. Let me do pointer option, laser pointer. The building that you can see here is our dream. So you can see that is all color because we dream of integrated in a building or in bridge or in many urban contexts solar cells that are efficient, but they're also aesthetically beautiful. So they can be color, they can be transparent in order to exploit all the surfaces that are around us, not just solar farms that we see around. So I will guide you through this talk with this idea in mind. That's why I always like to bring this photo as first one of my presentation, and to see what is our dream, how we would like to see beautiful solar cells integrated in our city. So I am a senior scientist in the Energy Research Institute that is part of Nanyang Technological University, and we are based in Singapore. And if you want to know more information about my research and our interests, you can find at this website. Okay, so let's see what is the general problem. So as we have seen in the last few years, so the climate change is a very strong problem in terms of is an emergency. It's something we really need to act quickly. This is why. Why? Because the human population is increasing very fast. At the same time, the emission of CO2 are also increasing very fast. And even if there was the Paris Agreement a few years ago with the idea of reducing the temperature of our Earth, the trend doesn't seem to go in this direction. So this is a problem because this is causing a lot of natural disaster. It's loss in terms of millions of dollars lost due to this disaster, and it also is the cause of tropical cyclone. So it's really is an emergency from all point of view to really make to switch from fossil-based energy production towards renewable energy production. And of course, in order to make this change very much influence, we need to act over all the kind of sector where we have where we need energy. So it goes to building, transport, heat, and industry. And of course, we need to have a combined approach in order to have an efficient reduction of the energy production all over the world. So 70% emission reduction can be achieved by detailed modeling of in introduction in each of these sectors. So when we talk about renewable, of course, there are many kinds of renewable, but solar is the one that is in a pole position. Let's see why. So if we go and have a look to what the nature has offered us just in front of us, what we can see here from this yellow ball is the quantity of energy that is produced by the solar. And if you can see here, just in this in this orange in the back here is the word usage per year. So all of these are the all renewable energy. So this one will never stop. While on these sides of the graph, you can see the coal, the uranium, the plutonium, are all the non-renewable energy. So this is also calling us for a call that this energy first or later we will finish. Why solar is the amount of solar energy that reach the planets is much more. It's 10 times more what we will 7,000 more of what we will need. So the real challenge is how we can make a good use of this energy, so 40 times more. So we really need to focus on how to convert this energy to make it this suitable. So just to give you an idea, if we have an efficient system, how much area will we need to be covered with solar panels to cover all the needed of the country. So if we are going to have a look to India, it means that is just 3% of the uncultivated land area of India that you can see. That it means just this spot that you can see here could be sufficient to provide all the energy required. So really, this makes the call for renewable energy, in particular for solar energy, as an urgent matter on different aspects. So this is a typical a photo of a solar panel, of a solar farm, where you can see that solar panels are all distributed all over big fields. And this is our beautiful campus in NTU, where you can see that on top of our rooftop, we have silicon panels everywhere. But even if there are silicon panels everywhere, and of course we need larger and larger device, just less than 5% electricity is generated of the actual need of NTU. So just less than 5% of this energy is generated by the solar panels that we have on the top. What does it mean? It means that we must have more efficient solar system in order to exploit more and more of the solar panel, of the solar energy that is reaching our rooftop and our land. So at the state of the art, more than 90%, say almost 95% of the solar panels that are commercially available are silicon solar cells. So silicon photovoltaics, you can guarantee high efficiency, long-term stability, has been in the market since almost 40 years. And as always, the panel usually they need to be changed after 20 years, no problem. The production costs, they are going lower and lower. So what are the problem with this? Why we need to look forward beyond this silicon photovoltaic? Because these silicon photovoltaics are very close to their efficiency limit. So this means that if we have higher efficiency, it means that we can generate it higher kilowatt per meter square. That is essential due to limited rooftop in urban area. So as I showed the example of NTU, if we have more efficient solar system, it means that on the same top rooftop that we have in NTU, we can, instead of generate 5%, we can get to 50%, ideally 100% of the energy needed by NTU, but we must have more efficient silicon panel. So let's have a look to this graph that is an NRL graph. So for people that are not familiar with this is NRL is an institute in US. So it's the National Renewable Energy Laboratory in US that is based in Colorado, and it set the standards and the certified value of all the type of photovoltaic technology, and not just photovoltaic. There is a section that is just dedicated to photovoltaic. So just to have a look, if you have a look to this graph, it tells you everything. The important is how to read it. So if you go have a look to this purple, so this is the efficiency of the solar system as function of the year. So basically we can see here that this one reported in purple are the one that guarantee the highest efficiency. So they are multi-junction solar cells based on a typical 3-5 materials. But these kind of solar cells are very expensive. And so it's impossible to think to have them integrated as rooftop or with our city or in solar farm. They are mostly just used for space application. Then we have the crystalline silicon solar cells, the blue one, that as you can see, they're around since 40 years. But basically, as I mentioned before, the efficiency stay constant. In the last 30, 35 years, we didn't see any major increment of the efficiency. And the other section is what we call the innovative technology, that are thin film technology, that the one that you can see in green and red. And specifically if we have a look to this part of the graph here, where we can see the red, this one here is the one that I've shown the fastest race, a steep race in efficiency. And there are the perovskite-based solar cells. So we have the perovskite single junction that they reach 25, even 25.5 and 25.6. And when they are in conjunction with the perovskite silicon tank, they exceed 29%. So 29.15 is the record value for the published article, but there are some companies that also have claim that they assume they have reached even 29.6%. So they are really getting closer to 30%. But what is the problem? That as you can see here, all these record values have been demonstrated for sites that are very, very small. So in this case are 1 centimeter square, in this case are much smaller than 1 centimeter square. And if we go back to the image that we had before, it's clear that if we want to integrate the solar cell in all our urban space and in solar farm, we must have large area. So let's try to understand what are the perovskite solar cells, why they are so important, and what we can do to bring this efficiency over large area. So hybrid metal halide perovskite material, they take their name from a mineral which was first discovered in the Ural Mountains by Gustav Reis, and they are named after this Russian mineralogist Perovsky. A typical structure you can see here, they respond to the general formula ABX3, and they have the main important optoelectronic property they have is They have a very good band gap tunability. They present a narrow PL emission that is very photoluminescence emission that is especially very important for light emitting application. They have a balanced diffusion length. It means that both electron and holes are balanced within the semiconductor materials. And they also, very importantly, they have a huge process versatility. So perovskite material, very different from any other superconductor, semiconductor that's been demonstrated up to now. It can deposit by solution process, by a slow die, so can be some, or by vacuum evaporation, or also by hybrid method. So perovskite offer cheap optoelectronic quality and versatile processable semiconductors. And these are unique properties to be found in just one class of materials. So again, this is the structure, the tetragonal structure of 3D perovskite materials. And just to give you a brief, very brief history of the advent of the perovskite. So in the 70s, there was the first synthesis and structural characterization of the hybrid perovskite solar cells. In the 90s, in the IBM laboratories in US, there was a lot of work in integrating this hybrid perovskite material in optoelectronic devices. But they were not still integrated inside photovoltaic materials. But they show very interesting material. It was just in 2009 where for the first time these perovskite material were integrated in a perovskite solar cells, and the properties of photovoltaic material were demonstrated. So the first time the efficiency of the solar cell was just 3.6%, but people still got excited because when you start with a new material, they already have a 3.6% as a first go is already a good start. And in 2014, 5 years later, there was the first demonstration of light emitting diode based on perovskite and also field emitting transistors. And during these years, so from 2009 to that, there's been a worldwide work on developing these solar cells and this LED, mostly based on both material innovation. So the perovskite materials were not just three-dimensional, but also two-dimensional, and also mixed-dimensional perovskite, and also on the device structure optimization. And they've brought to now 2021, where we have a single perovskite single junction reaching an efficiency of 25%, and as I mentioned before, perovskite on silicon tandem that well exceed 29%, they're reaching 30%. So when I mention perovskite material innovation, what do I mean? I mean that this is the standard 3D perovskite material. And when we change the organic cation that we have in the middle with a long chain, we can basically create interlayers of perovskite. These perovskite, of course, have a different dimensionality. So it's not a 3D structure, but this is more a layer structure. So it's what we call a 2D material. Or maybe changing the arrangement of the tetrahedron, we can change also the changing the emission of the material. So the nice thing is that, and during the year, many kind of perovskite have been studied. So with layered dimers perovskite, as you can see here, double structure perovskite, changing mostly the cation and the ion, and also the middle ions like the lead in tin perovskite. So also it's been demonstrated that it can be material can be bulk, it can be nanostructure, so you can have nanoplates, nanorod, nanoparticle, or even core shell nanoparticles. So the versatility demonstrated in this material is really exceptional. And also, as I was mentioning before, by changing the components, so in this formula ABX3, A is the cation, X is the halide, and B is the middle ions. Changing the cations and the halide, you can you can continuously change the colors of your material. So for example, this series can be obtained just changing one component, the Halide component, you can tune easily the colors, and also with a very high PL/QI efficiency. And at the same time, with a proper structure of the perovskite, you can also go all the other way around. So all a broadband emission, so combine all these colors together and have a very broad emission, working on the structure of the perovskite. So just to summarize, the metal halide perovskite have been found very interesting application in many different fields. In photovoltaics, and when I say photovoltaics, I talk about solar cells that are integrated in building integration. They used for tandem, so it's a multi-structure solar cells with silicon, but also with other low bandgap material, flexible device, hot carrier solar cells, as detector for X-rays, X-ray scintilation, but also for quantum device. Very recently, there have been few works in where perovskite, they're also used as a quantum source and quantum detectors. They've been used in a neuromorphic device for computing application. Last but not least, for all light emitting applications where the LED-based perovskite have reach efficiency exceeding 22% and very, very high color purity. So just in terms of PV, I summarize, this is just for photovoltaic solar cells, which are the main kind of solar cells that we look at. So we have the conventional type, these are the opaque, that they usually are the one that guarantee the highest efficiency. We can have the semi-transparent, where we change usually the top electrode with a semi-transparent electrode, colorful perovskite solar cell that can be achieved with a high variety of methods and approach, flexible, where we can have since it's a low temperature process, we can have they can be built on plastic substrate, perovskite on silicon tandem, and perovskite tandem. So with all these kind of solar cells, the idea is always the same. So that we want to maximize the PV utilization worldwide. It means that the different kind of solar cell that I showed to you, each of them, it can be customized for a different kind of application. And this is the only way to maximize the utilization of PV. So different kind of solar cells be used in different contexts. So for example, in a solar farm, we might need the opaque solar cell that can guarantee high efficiency. If we want to integrate our solar cells in a building, we may need the semi-transparent. If we want to aesthetically beautiful solar cells on a bridge, like I showed in my first slide, we might need the color one. But in order to maximize, this is the three main things that we always need to have. We have to keep a low production cost, high efficiency, and the process should be developed over large area. So these are the three main requirements that they build the maximization of PV utilization in our both urban and countryside context. So in NTU, as I mentioned before, and with the research team that I'm coordinating, we are focusing on the scale up of perovskite solar cells. Most of it, so as I mentioned, the record has been demonstrated with size much smaller than 1 centimeter square. And in order to scale up to few centimeters square and even larger centimeter square, like the standard solar panels, different approaches have been demonstrated. So some stuff can be done by spin coating, or like slow dye, as shown here, and also with a vacuum and hybrid process. In particular, we are focusing with my team, we are studying the vacuum-based processes. And why we choose vacuum process? Because it's a well-established industrial technique. So all the OLED that you see in your mobile phone or your screen, they are all processed by vacuum deposition. So it's already well established in many industry. like Samsung, like Philips, all the main, they're all based for their display on the thermal evaporation. They can guarantee high quality thin film with low roughness, high purity, and uniformity over large area. That is a challenge instead for solution-based process. Then is a solvent-free fabrication, is intrinsically additive, so I can build one layer on top of the other, and is conformal, so it means we can deposit it over even rough surface, and this is particularly important for the tandem, and it can go on flexible substrate. So which is our approach? The roadmap to high efficiency over large area is basically we develop the architecture over for small solar cells. So we work on the active layer engineering, interfacial optimization, surface treatment, light management, everything on the small cell. And then we design the modules, and we have a proper design of the module in order to go to large area. So let's go and see this in details. So in terms of step-by-step optimization, when we started with thermal evaporation, of course, we control the PBI2 to MA ratio by controlling the temperature of evaporation, and we choose the condition which guarantee the highest efficiency and the best quality of the perovskite. Then we optimize our charge extraction layer, and in this case in particular we moved from tin oxide to tin oxide with PCBM to improve the carrier selective extraction. And then we treat our perovskite with the MAI and potassium acetate in order to improve the film quality, and as you can see here the lifetime increases, and also this is a transit absorption that also show a significant increase of the lifetime. And what is nice of this treatment that we developed is the development that this treatment, it goes all through the thickness of the film. It's not just a surface treatment like many others, because we can see that all along the cross section we increase the size of the grain. And also some tough seams measurement show that the potassium, that is the green line that you can see here, it goes through all the thickness of the film. So this is our roadmap that we have. So we started after optimizing the stoichiometry. We start with the efficiency on 19.3%, as you can see here. After we treated our perovskite, we reached 19.91. And when we did a proper light management, that means putting the right anti-reflection coating, we reach an efficiency exceeding 20%. So this is just to summarize our roadmap to high efficiency. So we started from 16% when we start with unoptimized Mali, then we work on the active layer engineering, and we reach 19%, and then the surface treatment and light management, we exceed 20%. So a similar approach, the one that I have shown you in detail, is for the NIP architecture, that is the one here. We have done a similar process also for the PIN, and we reach efficiency around 20.6%. And then just to give you an idea that these values for the thermally evaporated perovskite are among the highest in the world. So the stars that you can see here for the two architecture are the value obtained by NTU group. So we are among the highest that we can get. So since all the process has been developed on the low temperature, we also could demonstrate flexible devices that, as I mentioned before, it can be interesting for many kind of application, and we reach an efficiency that is 19.4, and these cells are also very resistive in terms of number of bending. As I mentioned before, this is all the optimization that we have done on the small area. Now we move towards large area device. So what we have done, the first thing, we have scaled our solar cells, keep the same square structure as the small one. We move from 0.16 to 4 centimeters square. So as you can observe in this JV curve, what is happening is that the current that you see here for the 3 cells is almost the same. And also the VOC and the voltage is the same. where we lose in the fill factor, so you can see the shape of our curve gets lower. This is mostly due to the sheet resistance of the substrate materials. And this is a problem that is well known, but what is nice is that no other method have ever demonstrated that when you scale from 0.16 to 4 centimeters square, you can easily maintain the same value of current and VOC. So with this in mind, we try to scale up our solar cells to even larger area, to 6 centimeters square. And what we can see here is that what we observe for small cells, that the current and the voltage stay the same, but we lose in terms of fill factor. And so in order to reduce this problem, we decide to use different shapes. So instead of square shape, to use rectangular shape. And for example, here we keep the length fixed and we change the width. And we can see that we can minimize this loss, but we move even further, that we show that actually if we scale up our cells, keep the width that here we found as a good compromise one, that it was 0.65, that we can see the red one here, and we just change the length, we can maintain, even when we scale up the cells, we can maintain the efficiency and the photovoltaic performance the same. So this approach helped us to develop our perovskite solar modules, to design the solar module properly. So we create subcells with rectangular shapes to lower down the resistance of the FTO. And the mini modules are serial connection to reduce the power loss. And we minimize the dead area, that is the area between one module and the other. In our first attempt, we use both laser and manual etch device, and we also study what happens when we have a different dead area, which is the subcell size that gives the highest efficiency. So what we can see that, like in this case, when we have 0.25 dead area, that is quite big, this is when we do it manually, the best width for the subcell is about 1 centimeter. But when we can minimize the dead area, actually having smaller cells can further help. So according to this, we develop modules in two different conditions. Using the first condition here, we realize mini modules that are 21 centimeters square with that they reach an efficiency of 18.3%, and this has been a world record for a bit, has been reported in different journals. We also show that all these, of course, it was not just one modules, but quite few modules that were consistently above 18%, with area above between 40 and 47 centimeters square. But the problem with this module that is the GFF, that is a geometrical fill factor, is about 72-75%. For people that are not familiar with that, the geometrical fill factor says basically how much of this module is covered, how much loss we have. So we just cover 75% of this, we leave 30% out. So of course, the more we want to cover, we want to aim to higher and higher geometrical fill factor. So we decide to have a laser screening, so where we minimize the distance between these points in the module. So when we have a full laser etched and we change the subcell design according to the graph that we have done before, we achieve the efficiency of 18.4, a geometrical fill factor around 92%. And this was done with a smaller area. The area was just 6.4 centimeters square, but the design was very, very nice and reproducible. This is also being reported by different newspapers. The nice thing is that the long-term stability of the thermal evaporated perovskite also seems extremely promising, having both for the NIP and PIN configuration efficiency, long-term stability exceeding 20-50 hours, maintaining an efficiency above 90%, and under continuous illumination, while we keep it at room temperature in a control environment of 30%, the cells can maintain over 90% of the efficiency for over 1.5 years. And here we're talking completely unencapsulated solar cells. So this proves that the thermally evaporated perovskites are more intrinsically stable than the normal spin-coated perovskite. And we further investigated that for the thermal stability, and we showed that the thermal stability, it means that the cells have been kept at 85 degrees for a time exceeding 5 months, and they maintain over 80% of the efficiency. And in this paper, we demonstrated the reason behind that is that the thermal evaporated perovskite, they grow intrinsically unstrained, and this is the reason why they don't lose efficiency during the aging. So as I was mentioning at the beginning of the talk, our vision, of course, is to have efficient but also beautiful solar cell that they can be integrated in a large variety of urban constant, as you can see here below. And so we also developed colored solar cells, and this is our standard architecture, where you can see that you have FTO glass. This is the charge transport layer. Then there's the thermal evaporated perovskite spiro, and on top of that you have opaque electrodes. This opaque electrode, it can be substituted, has been substituted with the silver FTO semi-transparent electrode. In tuning the thickness of these electrode in a range between 220 and 115 nanometers, we have been able to change the reflection peak, the reflectance peak of the light coming into the cells. This has allowed to change the color appearance of the cells very consistently. As you can see, the cells show bright colors, and this is the color distribution of the cells with different thickness of just the top electrode. The cells inside are exactly the same. The thing that we just changed the top electron and not the active material allow us to demonstrate cells with a consistent efficiency for the different colors. So for the different colors, the cells are all about 16% with small variation. And this is very unique because usually different approaches have been demonstrated to prove color solar cells. They also always sacrifice the efficiency. With the same idea to go larger, we also demonstrate color mini modules that where the efficiency is still limited by the sheet resistance of the TCO. So we achieve 11% over 16 centimeters square. So as conclusion, I would like to say that thermal evaporation is a promising route to take perovskite to commercialization for three main reasons. The first thing is that we have shown that this perovskite by thermal evaporation can show a very good thermal stability. We have shown a very good scalability, not just because we achieve very good efficiency for our own modules, but also because if we compare how the efficiency, the worldwide highest efficiency achieved by thermal evaporation is about 20%, how we scale with the size, we can see that even if we will not change anything, at 6 inches, that is the typical size of a silicon wafer, we can reach an efficiency of about 17 or 18%, which is very promising. So this is the team that has been working, the thermal evaporation and large area solar cell team. And you can see that, this is most of the work that has been presented today. Dr. Lija is working on the thermal evaporation together with Dr. Enke, Dr. Elina on the thermal stability, and Dr. Wang Gao mostly on the color solar cell that you have seen. And of course, Ariane is part of a big group, and this is just one team within a big institute, and the director of the institute is Prof. Subbu Maisalkar, that is leading the institute towards the excellence. And also we need to thank also Prof. Ripan, we have Enk and Soshi and Tishisam. These are from NTU, beside Prof. Hank Bolling, that is from Valencia, but is our long-term collaborator. And you can see here Prof. Michael Gratzel, that before COVID was used to visit us regularly. And these are some of the people working on perovskite. Not all, because we have even more than that, but just to give you an idea that all the work that you have seen is done all by my team, but we are part of a big institute. And this is a picture of Singapore and our beautiful bay, and this is time for question.
Yeah, it was really one of the wonderful
Thank you.
Thank you very much. I hope you
Very nice.
enjoyed.
So can we take a few questions?
Yeah, sure.
Yeah. So the first question is, how much it is eco-friendly? So
Okay, this is an interesting question, because of course the perovskite materials are based on lead, but so this is some concern with lead. But at the moment, it's been demonstrated by many different groups that the amount of lead, since these perovskite cells are very, very thin, the amount of lead that is present in a typical perovskite module is not comparable with is comparable with a typical silicon modules that has lead were for all the soldering. So lead itself doesn't seem to be a big issue. It is more eco-friendly than other processes that require high temperature processing. So there are still things that they can be improved, but this state of the art is it is quite eco-friendly.
okay.
But there are still open questions.
Yeah. So another question is, is perovskite nanocomposite may have higher efficiency for solar applications as
Sorry?
Is perovskite nanocomposite may have higher efficiency for solar application as the nano size brings large surface area?
Sorry, I didn't understand the question.
Okay. So again, I'm repeating. Is
Yeah.
perovskite nanocomposite may have higher efficiency for solar applications as the nano size brings large
Okay.
surface area?
Okay, so there have been different attempts for perovskite. So for perovskite solar cells based on perovskite quantum dots, but the efficiency are still higher with the bulk film, because also the nanocomposite nanostructure, they bring a lot of defect on the surface that they can also limit the charge transfer within. But they will be potential to be developed. But at this time, they're not giving higher efficiency. Actually, the bulk is giving better efficiency.
Yeah, there is another interesting question. Can some light absorbing materials like pyrrole, uh, phthalocyanine, and chlorine, if composite with perovskite, increase the efficiency of the solar cell?
Okay, there are few works on that in combine the perovskite with with some other materials, and mostly either they need to be complementary or they need to have a very nice charge transfer so they need to absorb in a light in a region, the light in a region where the perovskite does not absorb, and they're able to re-emit where the perovskite needs to be absorbed. So in principle, it's something that it can be explored, but still good material to work as that they are efficient in absorb and re-emit with it is compatible with perovskite. It's not been demonstrated yet, but yes, there is space for that.
Another question is, by changing the cation and anion site of the perovskite, is it possible for effective increase or decrease the efficiency of the solar cell?
Yes. Yes, absolutely. Yes, this is most of the work. So when I was mentioning about composite perovskite in, material innovation, is basically changing the cation and ion size. That is, people are looking for the best composition in terms of stability, in terms of widening the absorption range. So yes, there is a lot of research on that, and it is possible. This is one of the main advantages of perovskite, because changing small change within the tolerance factor of the device structure, both changing of the anion and cation side, can lead to a material that are stable and they are efficient, the perovskite.
Yeah.
For example, a big moment for perovskite research was when people shift from the monocation to triple cation. So it means that there were 3 elements, so methylammonium, cesium, and formamidinium inside the cation, and they give stability and to the perovskite, and also shift the band gap, and also, of course, mix halide at the same time.
Yeah. So another question is, how much improvement in electron and hole mobilities for transistor fabrication using perovskite versus silicon?
No, still they are still not comparable. I mean, perovskite transistors are improving, but they are still lower than silicon in the state of the art. But again, they are promised. They're on the way, but it's still not at the moment. They are not competing yet.
Okay. So another question is, which kind of perovskite is better for solar panel? Is it double perovskite or metal hybrid perovskite?
Metal hybrid.
Okay. And this is in continuation. And
Hmm.
what combination of magnetic saturation and dielectric properties provides the highest efficiency?
It's not just that. Is of course the electric properties are important, but it's mostly also the absorption coefficient and the morphology, because they need to be defect free, and the band alignment between the charge extraction material that guarantee the best efficiency.
Okay. So
Interface recombination, yes.
yeah. So next is, can we have achieved the efficiency of lead-free perovskite quantum dots in solar cell more than perovskite quantum dots?
No, it may not be demonstrated yet. Not yet. And it's possible it could be, but the research is not there yet.
So another question is, are the perovskite layers truly 2D or they stacks of 2D layers?
Are the perovskite truly 2D or they are stacks of 2D layers? In a way, they can be both, because they are so we call 2D even when we have a stack of 2D layers, and it depends from another number that is M, that it tells you how many layers you have in your 2D structure.
Okay, so another question, which are the main cause of performance decrease of perovskite solar cells in large area devices? And
Which is
in
the main
different
case
kinds?
of performance decrease of perovskite? Okay, so mostly is given by the charge transport properties of the transparent conductive material. So the solar cells are built over a material that is a substrate, right? When you have the substrate, you have glass FTO. This FTO is called transparent conductive material, that is oxide, and this material, they have are relative low horizontal conductivity. So when it goes to large area, this become more dominant.
Okay, so another is, please share some information about light induced structural changes in perovskites and its impact on their performance in solar cell.
Uh, this can be very dependent on on the composition. So the light can induce an internal degradation, interface degradation. It can induce heat inside the perovskite. So it's a combination of factors.
Okay. And the last question would be, organic materials usually have poor photostability. Are these solar cells durable?
Are increasing. Again, a lot of work on the material optimization in terms of changing of cation, ion, halide, and the cation are helping to improve the stability, the photo stability, and the progress that they've been observed in the last couple of years are really impressive. So at the state of the art, they are much better than the organic materials, but they are not, they have not shown 20-year stability yet.
Okay. So in terms of efficiency, can you compare can you compare graphene-based solar cells and the metal halide perovskite with solar cells?
I think that fully graphene based solar cells, they're not, I'm not aware of a very high efficiency with that. So I think perovskite is absolutely higher with that.
Yeah, a few more questions are coming. So are you comfortable now? So can I ask?
Yeah, sure.
Okay. Do you think that thermal evaporation technology will be suitable in the future in order to scale up the device area?
Absolutely, yes.
Okay. What are the options of efficient whole transport layer other than Spiro MEOTech?
Yeah, there are few PTA. PTA is one of the materials. There is also some inorganic materials. There are many groups that they synthesize their own materials. So at the moment, spirometad is the one that is giving the highest performances, but there are quite few options, both organic and inorganic.
Okay. Okay, so I think all questions are over. We still some questions will come, then we will forward to you. Yeah, so finally, I take this opportunity to thank everyone who has helped in laying the foundation of this seminar. So on behalf of Embedded System and Robotics Research Group, Department of Electronics and Communication Engineering, MIT School of Engineering and Technology, and Institutions Innovation Council, MIT University, Uttar Pradesh, Noida, and my own behalf, I extend my sincere gratitude to our Honorable Founder President Dr. Ashok K. Chauhan sir for giving us an ideal platform and motivation to organize such events. I express my sincere thank you to Honorable Chancellor of MIT University, Uttar Pradesh, Dr. Atul K. Chauhan sir, for his constant support, guidance, and motivation. I now express my heartfelt gratitude towards Professor Dr. Balvinder Shukla Madam, Honorable Vice Chancellor of MIT University, Uttar Pradesh, for constantly inspiring us to strive better. I am feeling so honored to express my sincere thanks to our keynote speaker of International Research Seminar on Innovation in Optoelectronic, Dr. Annalisa Bruno, Senior Scientist, Energy Research Institute, Nanyang Technical University, Singapore. I am really obliged by your gracious presence. Thank you, Dr. Annalisa, for accepting our invitation and sparing your valuable time to deliver a wonderful session. Thanks a lot.
Thank you to you all. Thank you for the very nice invitation, and thank you for all the questions. That has been very nice, the whole nice presentation. Thank you.
Further, I express my sincere
Introduction.
thanks to Professor Dr. Manoj Kumar Pandey sir and Professor Abhay Bansal sir, joint head MIT School of Engineering and Technology, for its constant support, guidance, and motivation. I'm also thankful to Professor J.K. Rai, head of the Department Electronics and Communication Engineering and chair Embedded System and Robotics Research Group, and Dr. Pradeep Kumar, deputy head Department of Electronics and Communication Engineering, for their kind support, guidance, and motivation. I am feeling so honored to express my sincere gratitude towards all the panelists, researchers, faculty members, colleagues, all the students and participants from industry and academia, from India and abroad, who has come forward and actively participated in this seminar. I sincerely thank to all my student volunteers, especially Pooja Gupta of BTech EC 6M and Anmol Malhotra, BTech EC Evening 6M, who have worked hard to make this event successful. Last but not least, I would like to thank the IT team for providing us an uninterrupted IT support. Thank you. So we look forward to all of you for similar cooperation in future too. Once again, thank you all. Namaskar. Thank you, Dr. Annalisa, for joining us and sparing your valuable time. Thanks a lot. And definitely, we are going to invite you as a keynote speaker in our next event. That is an international conference on signal processing and integrated network.
Okay.
That is going to be held in the month of August. So we will
Okay.
right soon. Thanks a lot for your nice
Thank
presentation.
you.
It was wonderful. It was wonderful.
Thank you. Thank you again.
Thank you,
Bye-bye.
Dr. Alisa Bruno, for giving a wonderful session, wonderful talk. So thank you
Thank
very
you.
much. Thank you once
Thank
again.
you.
And definitely in future we'll have some collaborations with you and your organization also. So thank you very much for sparing a valuable time with us and giving a wonderful presentation. So thank you very much.
Thank you. Thank you again.